So, hello, I am Meetakshi, and I am currently working with the Azure Files team at Microsoft India. And I'm going to be presenting some eBPF scripts that I have developed at Microsoft, which can be used for analyzing performance issues on the Linux SMB client. So the agenda for the talk, it's right here. We'll quickly have a background and gather some context about how eBPF works, what are the current diagnostic tools at our disposal. And then I'll introduce the new tools, how they're implemented, and a quick demo. And then we'll move on to a case study to see this tool in action and how it helped me in some client-side latency analysis. And then I'll discuss the Always-On Diagnostics project, which the Azure Files team at Microsoft is going to undertake. All right. So for the background, here are some of the debugging tools that are available for the Linux SMB client. There's procfs files, which is debug data and information about open files in open files, and some statistics from the client in procfs if stats, etc. Then there is static trace points, which are debugging statements that are already added to the code by the developers. And there is also a way to do dynamic tracing using tools like tracecmd or trace-BPF or perf. They don't need to have any change in the client code. You can insert instrumentation point without rebuilding or recompiling. Then there's strace, which basically traces the system calls that are made by an application. And then there are a few others, the lsoff command, the ss command. You can use tcp dump, wireshark, and maybe gdb as well. So now, what exactly is eBPF and how it comes into the picture? So eBPF basically helps run sandboxed or event-driven programs inside the kernel, so which means that we can run these programs and add additional capabilities to the kernel without having to modify the code. And these programs have a low overhead as well. So by event-driven, I mean that whenever a certain hook point is hit by the kernel or by the application, these programs get executed, and we can collect the data accordingly. Now, the kernel expects the eBPF programs to be loaded into it as bytecode. So how does it actually work? You write the eBPF program in the user space using tools like maybe BCC or libbpf trace or BPF trace or libbpf. These are then loaded into the kernel. The bytecode is loaded into the kernel using the BPF system call. And after this, the eBPF verifier basically verifies the loaded code. It checks that you're not running an infinite loop, or or you're not doing a very out of memory bound access, stuff like that. After that, it is compiled to a machine-specific instruction set, and whatever hooks you have defined, you can hook onto any trace point or a system call, or whenever you enter or exit any kernel level or user level function. So once everything is done, once you have attached your program to certain hook points, you can start pushing data from the kernel probably into something called eBPF maps, and you can read that data from the user space or within the kernel as well. These eBPF maps are accessible both in user space and in the kernel. So for more information, you can refer to eBPF IO and how exactly eBPF works. Now, once you have a eBPF program and you have compiled it for a certain kernel version, you would want it to run on other kernel versions as well. Yeah, right? So we need to have portability. Now, we know that the kernel types and data structures are in flux. They can change. So something that works maybe on kernel version X might not work on kernel version Y because there's a certain field in a certain structure which moved to a different offset, and then your code doesn't work anymore. So how to address this? BCC navigates this by just shipping Clang with the source. So whenever you write your code, whenever you create an eBPF tool, there's Clang shipped with the binary. You just do compilation on the fly for that particular machine, pull in the kernel headers, and yeah, that's how you tailor the compilation to that kernel version. But this might not be very good because, number one, you have to ship big fat binaries with the source. And especially in production systems, when you need, there might be a large compilation overhead, which might not be very desirable. So how does BPF core address the same problem? So BPF core stands for compile once, run everywhere. You compile the program once, and you should be able to run it everywhere. Some high-level mechanics about how this works is the kernel can generate something called BTF, or BPF type information, which is a very minimal information about what data structures that are present in the kernel. And then Clang, with some extensions, can compile your pseudo eBPF code, pseudo C eBPF code, to have something called relocation information. So it might have information about for example, if you're trying to access some field in a particular structure, the Clang might have information that, OK, this is the name of the field that you are trying to reference, and this is the type. So if the field moves around, if it goes to a different offset, it doesn't matter because you already have that information that, I want to access this particular field in this particular structure. So it doesn't matter where it sits anymore. I can show a diagram in the next slide, which might be able to explain this better. So now you have the BTF type information, the BPF type information, and some core relocation information from the bytecode that was generated by Clang. BPF loader basically combines this information, the BTF from the kernel, plus the core relocation information from the user program, and it can adjust the object code to be so that it's tailor-made for that particular kernel version. So, and your BPF is basically, it looks like the kernel will feel like the BPF is compiled for your kernel version, basically. So additionally, one more important advantage that BTF provides is that this type information is exposed to the user as well through sysfs, and you can just easily create a C header file out of it called vmlinux.h. You can import vmlinux.h and start using the kernel types in your code without having to import any other header file at all. So that's also pretty useful. So this is basically a very rough schematic that shows how BPF core relocation would work. So if you have a BPF program that tries to access some field in some structure, when you generate the object code via Clang, you have some relocation information that is generated from the compiler itself. You use the BTF information that are in that particular kernel on the target host. You adjust the compile BTF code. And then even if your structure in kernel version A was maybe at offset X, and in kernel version B was at offset Y because a new field was installed, it wouldn't matter because your code would already be tailor-made for these kernel versions. So now, one thing I missed. So libbpf is a library which provides this facility. It acts as a BPF loader, stitches the BTF information and the relocation from the Clang together. And libbpf bootstrap, it's a project on GitHub which sets up everything for you. It has the make file, it has all the dependencies, so you can just start writing libbpf code and don't have to worry about the setup. So this is what I used for developing these tools. Now, we'll go to the new eBPF scripts for the Linux SMB client. Okay. So the scripts are SMB slower, SMB VFS slower, and SMB VFS IO Snoop, and they were inspired by ext4 slower, which I think Brendan Gregg has also talked about in his blog. There is already some slower scripts for NFS, ext4, and other file systems, but they only trace, I think they only trace a certain subset of operations. I think they trace read, write, open, close, and a few other calls. But SMB slower, SMB VFS slower, et cetera, they trace all possible SMB operations that can happen on the client. Now, so SMB slower. So SMB slower traces all SMB operations that are slower than a particular threshold. This threshold is configurable. You can provide it while you're running the script. And I guess this depends on how you look at it, but if you see that VFS sits at the bottom layer, then, VFS sits at the top, then maybe SMB slower works towards the bottom end of the SMB layer in the client stack, towards the network side. So there's a user space application which performs a system call. It enters the kernel space and maybe just gets routed to the VFS. And the VFS makes some calls to sifs.ko. And after that, once the request is ready to be sent to the server, SMB slower is going to trace the latency, basically the time taken when the client sends a request to the server and the response is received back. That is what SMB slower is going to track. So here are some features. Traces all SMB operations, latency from issuing the request over the wire and getting response back from the server. And it can be specified to trace a particular SMB command or a particular process ID only. And you can also specify a threshold for the minimum latency to be traced. So for example, here, I have given -P1206, only track this process ID, -C5. So there is a mapping for the SMB command with certain numbers. So command 5 means SMB create. Only track create request for this particular PID, and M5 means only track latency or only track create requests with latency slower than 5 milliseconds. Now, here is how SMB slower is implemented. OK, so there's a request that comes to sifs.ko, and every request that needs to go over the wire will always have some message ID allocated to it. And this happens in SMB2 mid-entry alloc function. So whenever SMB2 mid-entry alloc function is exited, that means the message ID has been allocated to that particular request. What I do is I hook onto the exit point of that particular function, and I store some information that is in this structure, maybe the session ID, what's the message ID, what's the SMB command, if the request has been compounded, et cetera. And in addition to that, I also store the time when mid was allocated. That means when this function was being exited, right? Now, this structure I store in a BPF hash map. The key is the mid-queue entry pointer, and the value is this particular structure that has been populated with the data that we just extracted from that function. Now, after everything has been done, we receive the response back from the server. Now the mid is being deallocated. Mid is being released. Once you enter this function, release mid, you still have access to this particular pointer. Now you use that pointer to query the BPF hash map and get this structured data. This structured data already has the allocation time of the mid. Now since you are releasing the mid, you have the deallocation time as well. You subtract the two, and that's how you get the latency. And you push everything in a BPF event array, which is then read by the user space component. So here's a quick demo. I'm not sure if it is big enough, but it's recorded, so I don't think I can zoom in a lot.
You can leave as a piece.
Okay. So now maybe you notice that some operations on the file share are taking a long time or are slow. So here I try to do an ls, and it's taking 4 seconds. I'm trying to create a file, and that's taking 4 seconds. And I'm trying to have a file descriptor open an already existing file, and that's taking some time too. So let's now try to ping the file server and see if it's a problem with the network latency. And ping time actually looks OK. So I'll try to use SMB slower to see what exactly is the problem. Now, by default, SMB slower is going to trace all operations which are slower than 10 milliseconds. And that is what is displayed as well. So now that I start performing operations, I can see that I can see the corresponding output there, and you can see that latency in milliseconds is always 2 for all of these requests. This is because I introduced an artificial latency in the server code, but now you know that the latency might be coming from the server side, so you can go and start investigating on the server side. So now we had a tool for the bottom end. Now there's a tool for the top end as well. You can trace slow VFS callbacks for SMB operations. It works at the top end, closer to the VFS. Basically, it traces the time when you enter a VFS callback and when you exit from it. So there's a system call comes to the which comes to VFS, and then VFS sends it to sifs.ko, and that's where VFS slower sits. Now, again, VFS slower can trace latency for VFS callbacks for inode operations, file operations, address space, and superblock operations. You can specify it to trace a particular process only. You can specify it to trace some minimum latency. Like here, SMB VFS slower is going to trace it only for process ID 1206. We'll trace it for 60 seconds only. That's the D switch. That's the D command line option. And only trace for inode and superblock requests.
The timers go in milliseconds as well as seconds?
Sorry?
All your times seem to be in seconds. It's very large.
Yes, this duration is in seconds. And
so you can't make it smaller? You can't specify milliseconds?
I can. So the latency is actually going to be in milliseconds, but this is the duration for which the script is going to be run.
Right, I know. And so can you set that threshold to less than a second?
You mean running the script for less than a second?
No, minus D 20 points. Never mind. Wait, keep going.
OK. I think it's just going to be whole numbers, so probably not, but I can make changes to the code and do that.
It's just your code that's
Yeah.
Okay, good.
So this is how SMB VFS slower works. This is another structure that is going to be populated and will be read by the user space. For example, there's an unlink request that comes from the application, lands at the VFS. Now it goes to sifs unlink. That's the VFS callback. As soon as it enters sifs unlink, we store the start time. NS means nanoseconds. So we store the start time, and you get the current process ID and thread ID, and you store the start time against this process and thread ID in a BPF hash map. Now, as soon as you exit from that particular function, you again poll the hash map, get the start time, and since you're exiting, you have the end time as well, and that's how you calculate the latency, subtracting the start and end time. And you push all of this information along with some more information. For example, delta millisecond is the delta microsecond is the latency, and this is when the request was finished. This is the type, basically the type of operation that was happening. This is the function which was being traced, and the name of the process which started this whole cycle. And then once you push it to the BPF perf event array map, it's going to be read by the user space component. So here is a short demo which shows VFS loader in action. So now you notice that deleting a file might be taking longer than expected, is taking longer than expected. So here I try to time it, and it takes 2 seconds. So we may not know where the latency exactly coming from, so I'll try to use SMB slower and SMB VFS slower to narrow down what might be happening. Now, when I use SMB slower, so M0 is going to trace requests which are slower than 0 milliseconds, which is not possible. So it's going to trace every single SMB request that is going on the wire. Now I try to delete the some file again, and latency looks OK. It's in milliseconds, in the ballpark 20 to 30 milliseconds, which is fine. So that's not our answer. Let's try to check what SMB VFS slower shows now. For some reason, I can't see the seek anymore. It's OK. So I try to trace inode operation, because if sunlink is an inode operation. And I do a delete again. And here, you see, CIFS unlink that is the problematic thing here. It's taking 2 seconds. That's also because I added some artificial latency into the CIFS unlink function. Now there's a third tool, SMB VFS IO Snoop, which can be used to trace IO at the VFS layer. Basically, you can get the return value from the VFS callbacks and the arguments that have been pushed, that were sent to certain VFS operations as well. So if there's a user space application which does a system call and goes to the VFS, this is exactly where VFS IO Snoop sits, just like SMB VFS slower. And I'll just show in a second what it traces. You can again trace address space, file, inode, and superblock operations. Can specify it to trace for a particular process only. Output in CSV format, that's all common. Now, if there's an open request, for example, from an application, and it goes to CIFS open, now, as soon as you enter the function, you populate certain events. So you populate, so as soon as it exits the function, you populate the return value from that function, and you populate the arguments that were passed to CIFS open as well. And the type, it's a file operation, function, the name of the function, and the task which started all of this. So you populate all of everything in this particular structure, and you send it to a perf event array, which is read by the user space. It's pretty straightforward compared to the other tools. Now, here is a demo. So I'm going to trace inode and file operations, and I'll do some stuff on the share. So I'm opening a file descriptor for this, so I can see the CIFS open and the name of the file which was being opened as well, and the inode. So I echo hello world, and I can see there's a write request as well. And now I try to close the file, and I try to cat it, and you can see the corresponding requests right there. Case study, a practical example of how these scripts can be helpful. There was some client-side latency investigation that I had to perform for my team. There's this FIO workload, which was opening and closing 32,000 files at random. This IO engine file open close is a custom IO engine. It just finds the latency of open and close. It doesn't do anything else. So it captures the latency on the client side, and this runs for 20 minutes. So what we saw was FIO client reported file open latency to be 4.39 millisecond, but the server reported a much lower number. So we wanted to pinpoint what is happening. Is it CIFS.q which is not able to keep up with these requests, or if there's something else that is happening on the client end or the server end? So that is what we had to find. The network latency was all good, so that could be ruled out. So I used SMB slower to trace operations that were happening on the client. And here is a excerpt from the output that SMB slower produced. So this output can basically tell us two things. Number one, the latency that was reported by FIO was 4.39 milliseconds. But if you see right here, it doesn't add up because it's always in the ballpark of 2.9, 2.8, or maybe sometimes 3, maybe 5 in between, but all of the pure create latencies were around this number only, and which led us to believe that the FIO might not be reporting the true create latency. Now, there is also one more thing to notice. There is SMB create with compound request as 0. That means SMB create it's not a compound request, it's an actual file open. And then there is SMB to create query info close in succession, which are compound requests. So these are revalidation calls that the client is doing. So you can see that there are creates that the application is doing, but these creates are also preceded by certain revalidation calls, create query info and close, which is also done by the client. So from the SMB slower output, we can see that the average latency from create, maybe it doesn't add up, but we won't know after we aggregate all of them. And there are revalidation calls that are happening before some create operations. So there are some questions to be answered. Number one, the create latency that FIO might be reporting might be bloated, but how? Maybe it's the revalidations. And if the latency is indeed bloated, what is the actual latency for file opens that is seen by the client? And does it match what is reported by the server? So we can actually process this output to get an answer to these questions. So my theory was that when FIO tries to open a file, since there are 32,000 files in the directory, what was happening was as soon as the FIO workload is run, it does a stat on every single file in that directory. And since there are 32,000 files, it's going to take more than 30 seconds, which is the caching time for the client. So as soon as you start issuing random file opens, it's possible that the entry might have been expired from the cache, and you might need to do revalidation again. So, but the application doesn't know that. The application only is issuing an open call, a create call. And it's the client that needs to go to the server and revalidate, and then send the file open. But the application doesn't know that. It's abstracted from the application. So what we believed was that maybe the latency is being bloated because FIO is aggregating the revalidation latency with the actual create latency. And that is something we can get from the SMB slower output because we can easily parse it using a Python script. This is something I wrote. So what we can do is we can get the pure creates, basically creates which are not a part of a compound request, because that is what the SMB slower output gives us. You find the pure creates, number of pure creates, and the actual latency from the pure creates. Similarly, you can calculate the latency from all creates, including the creates that are coming from revalidation. So once you get the pure create latency and you get the number of pure creates, the first theory is that FIO might be aggregating the pure create latency with the creates from the revalidation latency. So roughly, since it's a compound request, the latency for the create and the latency for the entire compound request is almost same, we can assume. So if you aggregate all creates that are shown by FIO, irrespective of being pure creates or being a part of compound request, and divide it with the number of pure creates, the actual creates that are happening, you can arrive at something close to something which FIO might be assuming is the actual create latency, which it might be observing. which is what happened. Latency perceived by FIO that we calculated from this script is 4.28 milliseconds, which is very close to the figure that FIO actually reported. Now, if this is the case, then what is the actual file open latency? It can be easily calculated by dividing the number of pure create latency with the total number of pure creates on average, which is 3.12 milliseconds. This is the actual file open latency, and this is what was reported by the server as well. So final thoughts. FIO was aggregating the revalidation time for a file with the time to open that file. And the perceived latency calculated via SMB slower output, 4.28 millisecond, is actually close to what was reported by FIO. So this kind of consolidates the first theory. Second, since this is happening, what is the actual file open latency that the client might be seeing? You can glean out the revalidation calls, and the actual latency would be 3.12 milliseconds, which was very, very close to what the server was also reporting. So this is this is a place where the tool came in handy and helped us analyze the application behavior as well. Now, let's talk about the overarching goal of this whole exercise. So the Azure Files team is, the North Star is something called Always-On Diagnostics, which is a daemon that will run in the background and periodically collect SMB and NFS logs. These tools are eBPF-based, so they have a very low overhead. So we can use them to basically look out for certain anomalies. Maybe the server has been returning some error code for a very long period of time, or maybe there's a spike in latency for an extended period of time. We can observe these this information which are provided by the eBPF scripts, and basically we will listen to various anomalies using the eBPF tools, and then we can start collecting output from certain debugging tools at our disposal, maybe dmessage or maybe CIF stats or several other things based on anomalous events that happen. Now, this would be particularly useful in cases where there are certain issues which do not repro very easily. So we need to have a daemon running in the background which can be smart about it and can capture these anomalies as and when they happen. So, and we'll also have some configuration operation to have a default set of anomalies to trace, and maybe the users can also tune it and enable more probes for the kernel. Yeah. So there's always also going to be periodic flushing of log bundles from memory to disk. This is another feature of Always-On Diagnostics. So this is the North Star that we are aiming for. This was the goal for this whole exercise. Yeah, that is all. For more information, you can look at these slides. And the current version of the tools, it's on my GitHub. It's available for everyone. And these are still in development, so they might not be the best version of themselves, but we certainly welcome all contributions and all feedback that we can get. So thank you.